welcome to this webinar that we will carry out today to talk about pressurization of escape routes. My name is Santos Bendicho. I am the head of the Smoke Control Projects Department. And today we'll talk about pressurization of escape routes. We will see the standards, the components that we need to consider to make an installation, and also some tips for calculation with our tool, with the QuickFind software tool. Okay, if there are some questions, you have a possibility to write the questions in the panel, and then after the presentation, I can answer the questions if possible. I will disconnect my camera because in order to have a better, more fluent information, and so we will start then with the presentation. Okay, so these are the points that that we will see today. We will talk about the pressurization. What is a pressurization system? We will make a short consideration about the old Part 6, 12.1 Part 6 from 2005, and considerations about the new Part 13, EN 12.1 Part 13 from 2022. This standard is yet being used widely in Europe. We will see the main differences between the old standard and the new standard. We will talk about the spaces to be pressurized. We will talk about the test and certification of the pressure differential kits, according mainly to the new Part 6 2022. We will do a review of the system components and pressurization equipment required for a whole system, and we will go for calculation using our QuickFind fund selection software. There are some references at the end, and of course, if you have questions, you can put it later. Okay, a pressurization system is a system that we use to avoid the leakage of smoke into the protected spaces, mainly the staircases, but also can include the lobbies and the corridors. And to do that, what we do is to blow air in the protected space typically to maintain a higher pressure in that protected space compared to the non-protected space, that is the fire room, fire level. Both when the doors are between the protected and non-protected space are closed, we want to maintain this level of full pressure, and when the doors are open, instead of maintaining this level of full pressure, the standard requires, European standards, to maintain a certain amount of air velocity, in both cases to avoid the migration of the smoke in that protected space. So the goal of the system is to maintain this protected space free of smoke, to allow the evacuation and to allow the firefighters to enter in the building through free of the smoke areas. So the aim, as I mentioned, is to establish this higher pressure in the protected space. The green part typically comprehends the staircase and can also include the lobby and also the lifts, both passenger or firefighter lifts, depending on the requirements for each country and the national regulations. It will be indicated if the lobby and or the lift has to be also protected, but in all the cases the staircase has to be protected. So we have this area A and B that are the protected areas, and we have the area C that it's the non-protected space, where we don't focus on which are the tenable conditions on that area C. We assume that this area will be full of smoke, but from that area we'll see that we also have to evacuate the smoke to maintain this performance of pressurizations. So mainly we'll have two scenarios. While the doors between the protected and non-protected space are closed, we will have some migration through the gaps between mainly around the doors. And so our goal is to avoid this migration of smoke through these gaps. But when someone opens that door, we will have the risk that this smoke will go into the staircase. So again, our goal is to avoid this migration in the door open condition. So we will have these two scenarios: door closed condition, where we need to maintain this level of overpressure. But we have to be careful, because too much overpressure could be dangerous. We need to provide enough overpressure to avoid the migration of smoke into this protected space. But if the level of overpressure on that green area was too high, then it will be difficult for people evacuating from the red area to open the door, because in addition to the force that the self-closing mechanism is doing, trying to close the door, we will have the force that the overpressure is doing on that door. So people who has to open the door has to make enough force to overcome these two forces, the self-closing mechanism force, but also the force considered provided coming from the overpressor. So if we have too much level of overpressure, then that will be risky, because people could not open that door. So we will have to also to limit this level of overpressure, and the limitation is related to the maximum force to open the door that is considered in the standard to be 100 newtons. This 100 newtons will correspond to a certain level of overpressure that depending on certain parameters, like the dimensions of the door, width, height, the force of the self-closing mechanism, the distance from the handle to the hinge, etc., etc. So there is not a fixed value of overpressure; it's a fixed value of force to open the door, but this force corresponds to different levels of overpressure. Okay, and we have the second situation, that is open door condition, when it's not possible to maintain this level of overpressure required by the standard. 50 pascals in the old part 6 and 30 pascals in the new part 13. So in that case, the goal is to maintain enough velocity in this door open to avoid the smoke going into the staircase. This is a video of how the system operates. Okay, if we have a building with, in that case, the staircase and the lobby protected for its space, we have one pressure differential kit providing fresh air in the staircase and or the lobby. Here we can see the firefighters' manual control, and we have grills or dampers to provide fresh air in the lobbies and in the staircases, pressure sensors to control this level of pressure, and then when we have a fire, the first point is that the smoke fire detection system has to be activated, and the fire detection system has to send a signal to our control panel. We receive the signal is activated by fire, and then the motorized damper of the airlet of the pressure differential kits are open, and you see how the pressure is increasing till we achieve this value, in that case 50 pascals for the all part 6, and then the level of pressure is controlled and maintained on that level. Okay. When doors are closed, we maintain this situation, but when the door is open, as all the air escapes through that door, it's not possible to maintain this level of pressure. You see how the pressure decreases to 10 pascals, more or less. In that case, the goal is to increase the capacity of the fan, provide more fresh air, increasing the velocity, providing enough velocity to avoid the smoke migration. When the doors close, again, we need to very quickly to return to the situation with 50 pascals control. Okay, this is our kitbox PDS, so that it's the main component that we use for the pressurization systems. Sorry. This is a model that we have also to explain also how the system performs, because in some countries there are also some requirements about natural ventilation. In that case, if we don't have pressurization in the staircase and we have natural ventilation from the stair, you'll see how the smoke is generated in one level, and the smoke is going out through the door to the staircase. So the risk here is that the people in the upper levels from the fire level, they cannot evacuate the building because they will die in case of going to this staircase. Will be intoxicated by the smoke. Okay, so even though this situation of natural ventilation is considered in many regulations, the risk of this situation is the contamination of the smoke in the staircase. On the other hand, with the pressure differential system or pressurization system, what we want is the opposite, is to maintain the staircase free of smoke. So both in the door open condition and the door closed condition, even if we have smoke, you see how by blowing air in the staircase and controlling the level of pressure, we don't have smoke in the staircase. It's very important, this air release that we have in the fire level to also to evacuate the smoke. Both in the door open condition, we increase the capacity of the fan, provide more fresh air to maintain enough velocity. The old standard, the old part 6, has different classes of systems depending on the a strategy of evacuation or firefighting intervention with different numbers of open doors and with different requirements for the air velocity in this door open. Sorry, and this is a real test that we make in a car park here in Spain, where in fact we were testing the performance of the jet fans ventilation system in the car park. But while we were doing the test, the people from the firefighters noticed that we had staircase pressurized, and they wanted to see how the system performed. And so we went to this the staircase that was pressurized, and even when with the door open, you see how when we went in, there's the lobby and the staircase was pressurized, so absolutely empty of smoke. So outside we have a lot of smoke because the machine was that generated the smoke was very close to this exit, but inside the staircase was completely free of smoke. Okay, once we have seen how the system performs, we will go to talk about the standards. We had in the past the all 12101 par 6. Remember the EN 12101 is the family of standard for smoke control, and par 6 is for specification for pressure differential systems. And we had in that case six different classes from A to F, depending on the building use and associated risk level. Okay, I will not focus on that because this is part of the history, but just to mention, now we have the new Part 13, EN 12101 Part 13 from 2022, that mainly it simplifies the calculation and the design, because instead of these 6 classes, that in fact it was a little subjective, because it was in the hands of the designer to think if the strategy was to be defended non-evacuation, so defend in place, or simultaneous evacuation or phase evacuation, etc. This subjective approach sometimes takes us to some misunderstoods in the design. So the new Part 13 is more clear. We have only 2 classes of system, and these classes in fact depend on some realistic or objective parameters of the building, the existence of sprinklers, for instance, of the existence of rooms between the fire room and the protected staircase to limit the movement of the smoke. So it's more clear if we have to apply class 1 or class 2. Okay, so and the standard also corrects some points that we saw, let's say mistakes or not clear points that we had in the Part 6 that are corrected in the new Part 13. Okay, and in addition has a better definition of the requirements of the specific components of a pressure differential system related to the requirement of other standards, etc., etc. So it's, let's say that it's more robust than the old Part 6. The classes that we have in the new Part 13 is class 1 and class 2. The main difference is in the door open condition. The rest of the requirements are the same. So we have the same requirement in terms of door opening force that we had in the old Part 6, 100 newtons. Just to mention, then NFPA 92 refers to maximum force of 30 levers, that it's 133 newtons. So in the United States they use this parameter. In Europe we consider 100 newtons. It's a parameter, could be one or other, but it's the parameter, and it was maintained from the old standard. Theoretically, it's the maximum force that an ancient people or kids can do to open the door. The pressure differential has been decreased from the 50 pascals that we have in the old standard to 30 pascal in the new standard. Okay, and the reason to do that was related to these 100 newtons, because as I have mentioned, these 100 newtons correspond to a certain level of overpressure depending on the parameters of the door, mainly the width and other parameters, but the width plays a big part in this calculation. And we saw that especially for doors with width around 1.2 meters, that in some parts of Europe are used, as the force of the self-closing mechanism is also related to that width. The bigger the door, the bigger the force. So when we made this calculation, we saw that the 100 newtons for that doors corresponds to a maximum overpressure sometimes below 50 pascals, around 40, 42, something like that. Okay, so according to that, it was for these big doors, it was not possible to maintain a minimum overpressure of 50 pascals. Okay, as the standard the OPAR 6 required, and at the same time to maintain a maximum force of 100 newtons that corresponded to 42 pascals. So that was a problem here. And in the other hand, we saw that the 50 pascals was too conservative, and with the 30 pascal was enough to avoid the migration of the smoke. To make a comparison, the FPA 92 from the United States has a requirement of for non-sprinkled buildings 25 pascals, and for sprinkled buildings 12.5 pascals. So in fact, with the 30 pascals, we are still in the safe side in order to avoid this migration of smoke in the door closed condition. For the door open condition, there is the difference between class 1 and class 2. And here it's very simple. For class 1 is 1 meter per second, for class 2 is 2 meters per second. This has not to be confused with these velocities that we had in the old part 6, where we had for classes A, C, D, and E that where the proposed was only evacuation, we had 0.75 meters per second. But for classes B and F, where the proposed was evacuation and firefighter intervention was 2 meters per second, the approach here is different. In the old part 6, the approach was that for firefighter operation, as the fire is fully developed, the velocity of propagation of the smoke is higher. Sorry, we have a question. Switch translation to different channel. No, it's only in English. I assume it's possible to switch translation to different channel. I don't think so. Sorry. I don't know if the tool has this possibility. Maybe with some AI you can translate immediately, but the presentation is in English. Sorry. Okay. As I was mentioning in the old part 6, the proposal of 2 meters per second was because for firefighters they have to make front of a fully developed fire. Here the approach is different. It's not for that cases. The approach here is no matter if it's evacuation of firefighters, the requirement of velocity is 1 meter per second or 2 meters per second. Mainly will be 2 meters per second, and only in some specific cases where we'll have some measures to mitigate the velocity of the smoke. We will reduce this requirement of 1 meter per second. There are also some requirements about the initiation time, the same that we have in the old part 6, and the same that we have generally for all the smoke control systems, 60 seconds. This is the time to have all the components in their operation position, and the operation time, that is 120 seconds, that it's the time to achieve the 30 pascals in the door closed condition, or the velocity in the door open condition when the system is started. There is also another requirement. This is in the changing situations. When we change from door closed to door open situation, the system has to react very fast. We had also this requirement in the old part 6. And in that case, for the real building, the requirement is 5 seconds. When we open the door, we have to increase the airflow, and in less than 5 seconds provide this bigger airflow. And when we close the door, we have to reduce the airflow, and in less than 5 seconds control the maximum the pressure differential. Okay, this is for the real build. We will see that the kits tested in the laboratory, the requirement is harder, is 3 seconds instead of 5. So regarding class 1 and class 2, class 1 will be considered in, let's say, class 2 will be in general, okay, where class 1 is not applicable if required by authorities having jurisdiction, and only in some specific cases we can consider class 1, that will be in building with the sprinklers. Sprinklers will make a reduction of the heat release rates or reduction of the smoke propagation, so it's clear that the velocity required in the door open condition will be less. Okay. It's also considered in residential buildings up to 30 meters or below the high-rise building limit in accordance with national requirements. Okay, because for residential buildings less than 30 meters, it is considered the first heat load that we have will be not so high like an office building, for instance, and in addition for 30 meters. Well, it was this requirement for standard residential buildings. I suppose not to be so strict or so hard in the requirements. And also in residential buildings, if there are at least 2 rooms between the fire load and the protected space without a fire. So we have, imagine that we have a staircase, we have 1 lobby, we have a second lobby, and we have the fire room. It's clear that these lobbies will make like a stop for the propagation of the smoke. And in fact, we have seen this in simulations that we have made. So in that case, the velocity of smoke will be less. So the velocity in the open condition required will be less. And class 2 when class 1 is not applicable or if required by authorities having jurisdiction. The main difference that we have between part 6 and part 13, and with this we can make a review of part 13, the grounds part 13. Generally speaking, part 6 talks about pressurization and depressurization. Part 13 only refers to pressurization because initially it was considered like that. During some time of redaction of the document, depressurization was considered because there was a requirement from UK where they use depressurization in some cases. But we saw that it was not so robust like pressurization, and the possibilities of using depressurization in terms of different configuration of staircases, lobbies, etc., was limited. So at the end, it was agreed with UK to not consider depressurization in this standard. In terms of the spaces to be pressurized, in both cases, staircases are always considered, but in the part 6 for class B and F, the lobbies were required to be pressurized, and also the lift shaft for firefighters. And also in the rest of cases, when we had a lobby connected to a lift shaft, it also was required to pressurize or the lobby or the lift shaft. In that case, in the new part 13, the spaces to be pressurized are referred to the requirements in the national regulations. So it's the national regulations who establish, depending on the building, if the lobby has to be pressurized, if the lift shaft has to be pressurized, etc., etc. The staircase, of course, has always to be pressurized. We have mentioned there are 6 classes in the old part 6, 2 classes in the new part 13. Okay, and the air velocity, as I have explained, was 0.75 for classes A, C, D, and E, and 2 meters per second for classes B and F, and in that case it's 1 meter and 2 meters per second for class 1 and class 2. But be careful, because the approaches, as I have explained, is absolutely different. Okay. About the pressure difference, I have mentioned we have reduced from 50 to 30 pascals. Some people could say, oh, this is a reduction of safety. It's not the case. It was, we analyzed it and we saw that with 30 pascals, it's safer now to avoid the migration of the smoke. Okay, and there is one parameter that is important to consider, that because there was also in the old part 6 a requirement of 10 pascals for classes C, D, and E. When the final exit door was open and the rest of doors connecting to the levels were closed, for these classes where we had a lot of people inside the staircase evacuation for simultaneous evacuation or phase evacuation, etc., it was this requirement. When all the doors between the staircase and the levels are closed and the final exit door is open, we need to maintain 10 pascals, and this in fact takes us to the highest airflow calculation compared to other situations. In the new part 13, this requirement is not present, this 10 pascal, but there is a requirement that has to be considered, that because as this door opens outside of the staircase, what we saw that the self-closing mechanism tries to close the door, but due to the overpressure in the staircases, in some cases we saw that this door was not fully closed. The system was not able, this self-closing mechanism was not able to close that door completely, and so if this door remains partially open, this is a big leakage of the system, and then the airflow that we need to put in the staircase to both maintain 30 pascals in the door closed condition or to maintain the airflow velocity in the open condition, it's higher than if that door was completely closed. So if our system is not able to, or if we cannot ensure that this door will be closed, completely closed, we have to consider the potential leakage that we have, or the potential opening on that final exit, okay, in our calculation. About the door force opening is the same, 100 Newton, there was not such change. About the response time, sorry, about the response time, we had in the old standard this requirement that for a system with variable supply fans or dampers controlled by pressure, the system shall not be used unless we can achieve 90% of the new volumetric requirements with 3 seconds of a door being opened or closed. This was a little confusion because when we talk about when we open the door, it's clear that we increase the airflow. So the airflow in the door open condition was typically the maximum one, so the 100, the nominal flow of the system. So it was clear in the door open condition that we need to provide 90% in less than 3 seconds and arrive to 10% a little later. Okay. But when we close the door, it's not clear. This requirement of 90% was not clear. We were talking about their flow in the door closed condition. This is something that it's not really controlled, because what it's controlling is the overpressure, not their flow, in fact. Okay, so this requirement was not clear, and it has been clarified in the new part 13 and the new part 6. Okay, the new part 6 for the systems kits tested in the laboratory. It's clear that when we open the door, we need to provide 90% of the nominal flow of the system in less than 3 seconds. But when we close the door, this requirement is not their flow, is to reduce the overpressure below 120% of the nominal overpressure in the door closed condition. Okay, so this has to be measured, and this has to be done in less than 3 seconds. Well, in the part 13, we have a similar requirement, but in that case, we talk about in less than 6 seconds, we need to achieve the new situations, the new conditions. Okay, so when we open the door, we need less than 5 seconds to provide, in fact, the air velocity in the door open. Okay, and this has to be measured in the real building during the commissioning. And when we close the door, we have to maintain to reduce the overpressure to the nominal one, in that case 30 pascals, in less than 3 seconds. So we have to measure also the pressure difference in 5 seconds, so the pressure difference in the staircase. About this final exit door, I have yet mentioned in the new part 13, if we cannot ensure in our design that the system will be able to ensure that this door is closed, fully closed, we have to consider that to be partially open. And when we do the calculation to maintain the 30 pascals in the door closed condition, or to maintain the 1 meter per second in the door open, too fast, in the door open condition. This is important to consider because here we have an example about the calculation if this door is considered fully open or fully closed. Okay, in that case, we have on the left side of the table, we have if the exit door is closed, you see to maintain the 30 pascals, we need to provide 2,569 kilometers per hour. And in the door open condition criteria, in that case 1 meter per second, class 1, we can make the calculation for class 2 also. It would be similar, would be more or less double the diesel flow, more or less. We have 8,205 kilometers per second. So the system, if you remember, their flows will be quite similar to a class A system of the old part 6. Okay, we will have typically this type of airflows around 8,000, 7, 8, maximum 10,000 kilometers per hour. Okay, but in the other hand, if we consider the exit door to be fully open, that will be the more safe consideration, that the door system, the self-closing mechanism or the overpressure maintains the door fully open. We have not really seen that in the reality. When we had seen these situations where this self-closing mechanism is not able to close the door, we have seen that typically the door remains 30% open, something like that. Okay, 20–30% open, not 100%. But if we had the calculation with the full area of the door, we'll see that the flow, both for the door closed and the door open condition, is huge. Okay, so this is something that has to be considered. As I will show you later during the calculation in our software, there is the possibility to consider this door to be fully closed or partially open. There is a percentage of opening that could be introduced in the calculation. Of course, this is a risky point in the calculation, because when we do the calculation, we don't really know which will be the amount of area that will be open. So if we want to be in the safe side, as we have made here, we can consider the door fully open. Okay. The thing is that after, when the building is done and the system is installed, there should be necessary to do a commissioning, and both the 30 pascals or 1 meter per second should be achieved and in the real condition. So then it's when we will know if the door will be 20% open, 30, 0, 10, etc., etc. So it's risky. In terms of the designer, it could be risky to consider a low percentage of opening of this final exit door. Okay, about the spaces to be pressurized. Mainly we had in the old part 6 these two considerations. Standards says that when we had only the staircase, or when we have a lobby, single lobby, that it's a lobby where we only have the door communicating with the staircase and the door communicating with the floor. Okay, in that cases it was not mandatory to pressurize the lobby. Okay, it was only mandatory to pressurize the lobby when we had a class B, class F system, okay, for firefighters. But also the standard says that if we have the configuration right, when we have the staircase, the lobby, and the lift shaft inside the lobby, it was mandatory to pressurize the lobby or the lift shaft. Okay, here let's see if I am okay. Here the point is that the reason to do that is if we have this type of lobby, if there was the lobby, in fact, it's indirectly pressurized by the pressurization of the staircase. The leakage that we have through that door leaks through that door. So at the end of the day, this lobby, it's 25 pascals above the level of the floor. Okay, it's an intermediate pressurization. So even though theoretically with 25 pascals, the risk of migration of the smoke through that gap will be very small. Okay, but even though we have some migration of the smoke, when we open the doors, the smoke will be evacuated from that lobby. Okay, that's why the old standard didn't require the pressurization of the lobby. In the other case, when we had the lift shaft, we cannot ensure the level of overpressure of that lobby, because the leakage, the air that is leaking through that door, will escape to the lift shaft, but also to the main level. Okay, so the level of overpressure of this lobby will be smaller compared to that case, and then there is the risk that the smoke leaks into the lobby and leaks into the lift shaft, and through this lift shaft leaks into the lobbies in other levels. That's why the old standard requires, when we have this configuration, to pressurize the lobby. Okay, if we pressurize the lobby, we don't have a smoke migration in the lobby, or pressurizing the lift shaft. If we pressurize this lift shaft, we have the same situation that we had before. Okay. Okay. So as I mentioned, the spaces to be pressurized are considered in the standard in the old part 6, but are considered in the regulation in the new part 13. So the new part 13 do not clearly requires you have to pressurize the lobby, or do you have to pressurize the lift shaft, or both. Okay, we always need to pressurize the staircase, and it's the regulation, national regulation, who has to explain, has to say if the lobby has to be pressurized, or if the lift shaft has to be pressurized, or if both has to be pressurized. The standard, the new part 13, says, okay, if you have the staircase and the lift shaft pressurized, for instance, that case here, you have to consider this. The leakage has to be from the lobby, the velocity you have to consider on that door, the pressure difference, blah, blah, etc., etc. Okay, so there are requirements of achieving the performance of the system for each one of these examples. So the standard gives examples, so but the regulation is the one who will mandate to use one or the other solution. Okay, we see that we have systems without lobby pressurized, okay, with or without the lift shaft, and with the air release from the lobby or the air release from the corridor. Okay, and we have we have systems where we also have the lobby pressurized, okay, and also the lobby and the lift shafts pressurized. Okay. Well, what do we have to consider about pressurization of lobbies? We have two possibilities when we pressurize the lobbies. One is pressurizing the stairwell and the lobbies of all the stories of all the levels at the same time. And the second one is pressurizing the stairwell and only the lobby at the fire level. Okay. With this example, for instance, if we have a system to pressurize the staircase, okay, and we have a system to pressurize the lobbies, okay, the first possibility will be to pressurize all the lobbies at the same time. In that case, we will only need, what we do typically in that cases is to consider a constant capacity fan to pressurize the lobbies during all the lobbies at the same time during the door closed condition, and when we have the door open condition with the two doors open, the door between the staircase and the lobby and the door between the lobby and the level, what we do is to increase the capacity of the pressurization system in the staircase, so the air that we are putting in the staircase, it's the one that is in fact used together with the air that we are blowing the specific lobby to provide enough velocity in the door open. Okay, but we maintain constant the capacity of this fan, because if we modulate the airflow, because in this situation what we do is a duct connected with grills on its lobby. Okay, if we modulate the airflow of that fan, increasing in the door when the doors open, indirectly what we will do is to increase the airflow that we are putting on its lobby. And this will increase the overpressure in the lobbies where the doors are closed, where the door is not open, and this will cause difficulties to open that door for people that is evacuating. That's why we pressurize all the lobbies at the same time. It is recommended to do it with a constant capacity fan and to increase the capacity of the fan from the staircase. This is a solution that for, let's say, low-rise building where we have the same configuration of lobbies is on the level, so the same amount of airflow in each single level, then it's possible to use it, because well, we need some commissioning time to adjust the flow that we put on its lobby through the grills. Okay, but it's possible to do it. If we don't want to, if we want to avoid this commissioning, or if the airflow that we have to put on each single level is different, or if we have a lot of levels, then it's a better solution to pressurize only the level where the lobby of the level where the fire is. In that case, this duct will be smaller because we only have to carry the airflow for one single lobby, not the airflow of all the lobbies. The capacity of the fan will be much smaller because this fan will be only for the airflow for one lobby. Okay, and in that case, we instead of grills, we will put motorized dampers, and we will put pressure sensors on each level, connected all of them through the main control panel, so that in case of a fire, only the pressure sensor of the fire lever is activated. The signal of this pressure sensor is sent to the PLC in the control panel, and this is the one that is used to modulate, yes, in that case, the flow on the lobby. In addition, this damper in the specific lobby has to be opened. This can be done from the fire alarm system or from our PDS control system that has a pressure sensor and has the possibility to open this specific damper, motorized damper, and also to open the air release damper, as we will see later on. Okay. Well, now we will see which are the components that we have for the pressurization, the equipment that we have. The first one is the pressure control. Okay, this is the main task of the pressure differential system, to maintain this control of the level of our pressure, to maintain this 50 in the OPAR 6 or 30 pascals in the OPAR 13 control while the doors are closed, and while the doors are open, to provide enough airflow, to provide enough velocity. To do that, to manage these two situations that we have, and and also to manage intermediate situations that we had, like we had in the part 6 when we have class C or class D, where we have in fact 3 situations. There are different possibilities. The one is dampers, barometric dampers opening outside to evacuate the excess of airflow. So we design our system for the airflow for the door open condition. Okay, we know that for the door closed condition this is too much. Okay, but then what we do is to install a damper at the top of the staircase that when the overpressure below the louvers of the dampers exceed the nominal overpressure, 30 pascals, for instance, then the louvers automatically, due to the overpressure, open and evacuate the excess of airflow. Okay, so this damper has to be calculated for this difference between the airflow in the door open condition and airflow in the door closed condition. One of the problems of that system is that okay, the airflow in the door open condition will be the maximum airflow of the fan. Okay, but the airflow in the door closed condition is something that we calculate, and I can assure you that will never be the one that you will have in the real building. Okay, because you will have more or less leakage in the building. So in fact, the system has to, in the door closed condition, the system is not designed to maintain a specific airflow. It's designed to maintain a specific pressure. Okay, so as we have to design or dimension this barometric damper for this difference in airflows, it's necessary to adjust during commissioning these dampers, or to have dampers that allow some range of airflow. Okay, and this is a risk. In addition, other risks of these systems with dampers is that they work quite good between 2 points, minimum airflow or maximum airflow. But if we have intermediate situation, as we have in part 6 for class C, D, or if we have intermediate situations as we have in part 13, if this final exit door it's not ensured to be fully closed, okay, then these dampers cannot properly operate in 3 positions. They operate properly in 2 positions, but not in 3 positions. Okay. So, well, it's not clear, these systems. We have also this possibility with dampers together with the fan to make like a bypass. And the system that it's widely used in most of the countries in Europe is a system with modulation of their flow through regulation of the fan speed from the signal from a pressure sensor. We have this pressure sensor that sends the signal to an inverter or a PLC, and the system modulates the velocity, so the capacity of the supply fan. While the doors are closed, we reduce the capacity of the fan to maintain this 50 pascals. Okay, in the upper 6, 30 pascal, in the upper 13, sorry. But when the door is open, as it is not possible, all the air escapes through that door, then the pressure decreases. It's not possible to maintain this level of pressure. So imagine the pressure sensor reaches 10 pascals. Okay, sends a signal to the inverter and says, oh, okay, I'm reading 10 pascals, and the inverter say, yeah, okay, but my set point is 30, so I need to increase the velocity of my fan. So sends a signal to increase the capacity of the fan. That's increase the flow, so the overpressure increase a little, so the pressure sensor say, okay, now I have 12, and we have the situation till the systems increase the velocity till it arrives to the maximum 50 Hertz and the maximum airflow capacity. Remember that in that case, the goal is not to maintain this level of pressure, the level is to maintain this air velocity corresponding to this maximum airflow. And the system has to be very, very fast, okay, because we have 2 risks here. When we have here, we have here, okay. This is in orange, we will have the nominal overpressure that we want to maintain, 30 pascals, for instance. And in blue, here we have the nominal airflow, the maximum corresponding to the door opening condition, okay. So and here we have the door closed. We open the door is open, we close the door, etc., etc. Okay. While the door is closed, our goal is to blow a little amount of air to maintain this level of overpressure. Okay. But when we open the door, okay, the risk is that the smoke goes into the staircase. So very quickly we need to increase the airflow provided in the staircase, because you see that the level of overpressure decrease. So this will be the risk of the smoke going into the staircase, and in that case we very quickly has to increase the flow of the fan to provide the velocity to avoid the smoke going into the staircase. Let's say that this is not a big problem, okay? It's necessary to do a fast regulation, a fast acceleration through the PID of the inverter, but let's say that it's more or less, let's say, easy to manage, okay? Of course, this will depend on the relation between the maximum airflows and the minimum airflow. The bigger the acceleration, the more difficult to be this acceleration, okay? The main problem in terms of these systems is when we have this door fully open and the self-closing mechanism try to close the door, we reduce the area of this door open, okay, and we are blowing a big amount of air. So as we have this big amount of air that is escaping through a small area, the level of overpressure will be rise very quickly, okay, in orange. So in that case, the risk is that the people who want to evacuate are not able to open the doors because we have a peak of our pressure. Remember that we have a 100 newtons maximum force to open the door. That will correspond around 40, 50, 60 pascals, depending on the door dimension. But these peaks could arrive to 100, 120, or even more pascals. Okay, so the system has to very quickly reduce their flow. Okay, to reduce the overpressure so that the time while we have this excess of overpressure is less than 3 seconds in the test system or in the 5 seconds in the real building. So to have a short period of time while we are not able to open the door, okay? And this is not so easy to do, okay? Deaccelerating a fan with the inertia that a rotating machine has, it's not so easy. We need some specific consideration, and this is the harder part of a pressure differential system to achieve this performance, okay? And this is mainly what the 12101 per 6 2022 has for the requirements. This is specifically that, okay, we have these requirements for testing. We had some requirements in the old part 6 related to this reaction time. Remember that we have this we have these two sentences. Both say that we have to achieve 90% of the new air supply requirements in less than 3 seconds, okay? And remember that the old part 6, sorry, it's an harmonized standard. So according to the construction product regulation, requires the CE mark for these pressure differential kits. In the same way that we require the CE mark for smoke extraction fans, for smoke barriers, for natural events, smoke control ducts or smoke control dampers, this standard being harmonized requires this CE mark. But the problem is that this standard that was published as harmonized standard in the official journal of the European Union, this standard includes the Annex Set A, that is the one that explains how to make the CE mark, and it's the annex that in fact makes the standard harmonized, okay? But the document do not have the rest of the other annex required to define how to test these essential requirements for those kits by the national notified bodies. So when we or any manufacturer in Europe has tried to go to the notified bodies, to the laboratory, to test these kits, they has told us, no, it's not possible to test because we don't know how to test. So notified bodies cannot provide the certificate of constancy of performance, so we cannot, as manufacturers, provide the declaration of constancy of performance and to CE mark our pressure differential kits. No matter if the kit it's a completely disaster or a kit is fantastic, none of us can test this kit, okay? And this was a big problem. In fact, sorry, there is some document from the European group from the notified bodies that states that the notified bodies, they cannot test this standard, and they say that the standard in fact is more a design standard than a product standard. That was the reason to start many years ago with, when we solved that problem, we say, okay, we have to do something. The first point is to make a standard defining how to test these kits, and then make this new standard harmonized, so replace the old part 6 by the new part 6 explaining how to test. But we also, as the all part 6 also gives requirement for design, installation, commissioning, maintenance, etc. We say, okay, but in addition to the test, the standard for testing the kits, we will need another standard for designing the systems. That is the part 30. The new part 6 2022 is the standard for testing and certification of pressure differential kits. It defines a test chamber with different possibilities, with the 3 types of kits, with barometric damper, with damper motorized, or with variable speed fans, okay, with different possibilities of additional leakage from the protected space, additional leakage from the non-protected space, etc., with pressure, with mechanical supply and air release natural mechanical. There are different possibilities, but this standard clearly defines how to test that kits. And the performance that we want to test is the same that I have explained before, is the reaction time. So we have on our left side, we had, sorry, here the door movement, the same here, door closed, we open, door open, we close, door close, etc. And we have, which is the, when we open the door, we see that we have to increase their flow, V is their flow, to provide 90% of the nominal flow in less than 3 seconds in the system that we test in the laboratory, okay? And when we close the door, we don't worry about their flow, we worry about the peak of overpressure. When we close the door, we know that we have this peak of overpressure, and again, the system, the requirement is to reduce below 120% of nominal overpressure in less than 3 seconds, okay? We have some time for door movement, or door opening time 1 second, the door is remain open 6 seconds, then it's closed in 3 seconds, etc. This is the functionality test that we have in the standard, and we have to carry out this test 20 times and measuring these parameters, okay, measuring this time of reactions to achieve 90% of their flow, and the time of reaction to achieve below 120% of the nominal pressure, and we measure 20 times. But before doing this functionality test, we do first a durability test running the system of 10,000 times, trying to make the system old, let's say, to damage the system. And we carry also the oscillation test, where this is the door movement. We open, and instead of remaining open and then close, we open and close, open and close, and open and close. And there is also something like we open, and when it's open, we partially close, and then we partially open. We make this oscillation test to try to make the system crazy. Okay, there are the systems, especially the ones that work with inverters or PLC. The electronic has to be very sensitive, and then the hard part of the test is to try to make this electronic crazy. Okay. Or with mechanical system like our pressure or barometric dampers to try to damage the system or to put the system under stress. Okay, once we have the test, we can, the laboratory states the certificate according to the 1211 part 6 2022, and this is what we have made for our Kitbox PDS and Kitbox PDS Smart. It's the same product with some evolution in terms of performance, and including the PDS lobby control, that is the control panels that we use for the pressurization of the lobbies, as we have seen before. The problem, let's say, nowadays is that from the European Committee of Standardization, we require to de-harmonize the old part 6 and to harmonize the new part 6. But it was not considered by the European Commission. This is because we had a situation in the European Commission where they want to change the approach of the certificate of constancy of performance. This is what is called the CPR acquis project, and we are now, let's say, during the last years, non-standard for products has been approved as harmonized because the European Commission want to change the procedure. And now we have this in great situation where we cannot harmonize new standards. If we write a new standard, for instance, for testing of smoke extraction fans, the part 3, we know for sure that with this new document will not be approved as harmonized, so will not overcome the existing document. So we had this situation where legally, according to the Part 6 from 2005, the manufacturers or the installers should provide a CE mark for the pressure differential kit. This is not possible because it's not possible to test according to this standard. Okay, but we have the possibility of testing voluntary to Part 6 2022, and at least to give a certificate from as manufacturer. Okay, and this is what we have done, and we have the certificate for our kits. In addition, as we before doing this test from Part 6, we previously have tested these kits in Poland, because Poland many years ago they were advanced and they, let's say, copied the draft that we were writing in the European Committee according to Part 6 2022. And they established a national certification procedure, and we tested many years in 2017 yet our kits according to this procedure. So we knew from 2017 that our kits will be able to pass this test for the new Part 6. But in addition, this Polish certification requires other certificates that are not in the Part 6 2022, that is related to the electromagnetic compatibility, to environmental resistant tests like cold, dry heat, vibration, dust, etc., etc. And this is also in our Kitbox PDS and Kitbox PDS standard. Okay. Other parts to be considered regarding the equipment are the standby fan. Okay. In the old Part 6, it was mentioned that if there were only one staircase in the building, it was necessary to have a standby fan with the same characteristics as the main fan, and the commutation in case of failure of the main fan has to be automatic. In the new Part 13, there is not such a requirement, because it was considered that the fans that we use are robust and they don't have this risk of failure. And it is not such a requirement, but even though it's a good practice, if the designer or the installer wants to do it, to provide a standby fan. Our systems are also capable of doing this commutation, and there are two possibilities when we install standby fans. One is to install them in parallel. In that case, it's necessary that the fans has a backdrop damper, so that the fan that it's not operating, that case we don't have a recirculation of air through that fan. Okay. The other possibility is to install in series. Okay. Here we don't need this backdrop damper and this type of insulation with a lot of space to be considered. It's simple, but be careful, because there's a fan that it's not operating creates a high pressure loss in the fan that it's operating, what it's called idling loss. Okay. And in that case, both fans will be with bigger power with motor that if we install with this consideration. So we have here, you see that we have the components that are part of the system: the supply fans, the variable frequency driver, the pressure differential sensor to control the pressure, and the standby fan when needed. You will see that we will include more things when we are passing the presentation. So next point is the air intake. Both standards, the old Part 6 and the new Part 13, has a requirement in terms of avoiding the risk that the air intake is contaminated by the smoke. Okay, if their air intakes are located, they should be located away from any potential fire. Should be located or on or near ground level to avoid contamination by rising smoke. If this is not possible, then it's necessary to, when we install, typically we will install in the ground level, that it's a place with less risk of being contaminated, even though it's necessary to have an air intake with a smoke sensor and motorized damper, even though so that in case of being contaminated, this system will close the damper and stop the fan. If we install this system in other levels, when there are more risks of being contaminated, specifically in the roof, we have to provide two independent and separated air intakes directed to different facades, so that each one with the motorized damper and the smoke sensor. here the performance is that we have the smoke sensors, okay, we have the dampers that initially are open both, and we have the fans. But if we have some smoke contaminating any air intake, these dampers are closed and the other remain open, the other damper remain open, sorry, providing the airflow, okay. Even though if both are contaminated by the smoke, both dampers will be closed and the fan will be stopped, but our system, and the standard requires that, says that the smoke sensor has to be resettable. That means that in some period we have to check again if there are still smoke present in any of the air inlets, and if the smoke has disappeared, we can reactivate the system. There are one question here. It is actual for lift shaft systems to inlets. In fact, should be the same, because the purpose is not rated for lift or as for a staircase. Okay, the goal is to avoid the putting smoke in the staircase or in the protected space. The lift shaft, it's a protected space. We will have the same consideration. The point is that maybe it's not necessary to have for each fan 2 independent air inlets. We can have a plenum for the air inlet all of the system, let's say, of the lift shafts and the staircases, and from that plenum we can take the fresh air not contaminated to provide both in one side on the lift shaft and on the other side and in the staircase. So it's not necessary for each space consider 2 independent air inlets. Maybe it's possible to do it with 2 independent inlets for the whole pressurization system. Okay, so about the ductwork distribution, okay, the preferred pressure differential system distribution is a vertical duct running adjacent to in the pressurized space. When the distribution ductwork is completely inside the staircase, the fire compartment, there is no requirement of fire resistance, okay, because ductwork is carrying fresh air, not a smoke. But when the distribution of the ducts passes through other fire compartments, it must be protected, or it must have a fire resistance and therefore be classified in accordance to EN 3501 part 4 regarding integrity and insulation. Okay, so we have both this in the part 6 and in the part 30. Okay, about the air supplies point, these are not parts of our specific components. These are part of the installation, but it's interesting to consider the requirements of the standard. The goal of the system will be to have an uniform distribution of air through the protected space and to prevent air passing directly from out of an open door as soon as it has been supplied to the protected space. So the recommendation that we had in the upper stage was do not install air supplies near doors, especially the final exit door. There was a requirement of 3 meters away from the final exit door. And to distribute the supply points as uniform as possible. Okay, each protected space shall be provided with its own dedicated pressurization system in terms of the kit. Okay, and the lobby shall have pressurization air supplied through the ductwork that is independent of the air supplied to the staircase. The corridors shall have pressurization air supplied from a duct that is separated from the lobby and the stairwell supply. In terms of the distribution of air, the reason to have a uniform distribution of supply points was to have a uniform distribution of pressure over pressure along the staircase. We know that we have the phenomenon of the stack effect. Okay, the higher the building, the more important the stack effect. The stack effect is due to the difference in temperature between inside and outside of the building. And for high-rise building, this could be something to consider. And one of the first measure to fight against a stack effect or to help to have a more uniform distribution of pressures is to have a uniform distribution of the supply points. The old standard has this requirement that for buildings less than 11 meters was possible to have one single point for supply, but for buildings more than 11 meters, it was necessary to have one supply point per each 3 levels. Do not to put supply points 3 meters the final exit door. And for lift shafts, it was necessary to have one supply point is 30 meters high. Okay, in the part 13, it's not mandatory to, we don't have these requirements, okay, because at the end of the day, the responsibility of the system is in the hands of the system installed, okay, so gives more responsibility to the installer. No matter the number of points that are installed in the system, if when we test, make the test, we pass the test, we achieve the 30 pascals in all the levels, we achieve the 1 meter per second in all the levels, and we achieve the reaction times, okay, no matter the number of supply points and where they are placed, okay. This is a problem for the designers, because when we make the designers, we could be more conservative. And then even though the new part 13 do not have these specific requirements about the position of the supply points, I would recommend to at least consider the recommendations that we had in the old part 6, okay, because they have demonstrated that they were robust. Okay, then we arrive to the air release points, air release systems. We know that during operation of the system, air will flow from the pressurized spaces into the accommodation, okay. The air will pass through the gaps or through the open door, has to be evacuated from this accommodation area, because we need this air release, because if we don't have this air release, imagine that this area is completely thick, okay, and there is no possibility for the air to escape from that building. Of course, when the door is open, the air will not pass, because if we cannot escape, we will not have air movement, or we will have a recirculation on that door. The air will pass through the upper part and will go down, will go back through the down part. Okay, so in fact, we will not have, so the net velocity will be 0, because we will have air entering and air going out, and we'll have a net velocity of 0. Okay, and when we have the door close condition the same, if the air is not capable of passing through these gaps, we will not have this pressure difference. We achieve pressure difference between two spaces when the air passes through a hole between these two spaces. If there is not this possibility of escaping, we will not have air movement and we don't have pressure difference. And we have seen this in simulations that we have done. Okay, so it's essential to have this air release. Okay, and this is also required in the old part 6 and in the new part 13. And in the new part 13, it's more detailed than in the old part 6 requirement for these areas. There are different possibilities. The first one is to have these vents in the facade of the building. Okay, these motorized dampers, flaps, louvers, vents, let's say. In case of these natural vents, it's necessary that if the facades can be affected by the air, then to double these vents into facades, so that and with a system reading the velocity of the direction of the air of the wind the air open or close the proper vent. Okay, we have these possibilities with this type of vents, and we need to open the vent in the fire level, not in the other levels. Okay, so to do that, remember that we have these PDS lobby controls where we measure the pressure difference in the level where the fire is, and then we can open the motorized damper to provide fresh air on the lobby if we want, and also from that control panel to open the vent in the fire level. We have also the possibility to do it with a DAC communicating all the levels, okay, natural DAC, okay, communicating all the levels. So we will have the pressurization of the staircase, pressurization of the lobby, and again, this DAC has to be provided with dampers to evacuate the smoke from the fire level. So in that case, we are not talking about fire dampers, we are talking about smoke control dampers, okay? Because the dampers on the fire level has to be open, but the dampers in the other levels has to remain closed in order to avoid the smoke going into that other levels. Okay, there are two different performance in terms of smoke control dampers: single compartment or multi compartments. If each of these levels it's a fire compartment, this DAC should be fire rated, of course, and this damper should be also fire rated, let's say, or EI, so multi compartment smoke control dampers. If we don't have this situation, imagine a car park where we have all the levels are one single compartment, then we can use single compartment smoke control dampers. And these dampers can be also opened from this PDS lobby control. There is one question. Hello, manual release through window. I suppose you mean manual operation. No, it's not possible. It has to be automatic. The opening of this window has to be automatic because we need this air release to ensure the pressurization. So we cannot trust that someone will open the window before evacuating the fire level. Okay, so the standard is clear on that. Has to be automatic operation of that window or damper or whatever. Okay, and specifically in the fire level, this is one of the reasons also that the system has to be activated through an I will talk later, through a fire detection addressable system, because we need to know on which level the fire is present to open only the window or the damper on that level. So for that reason, the system cannot be operated by manual call points that someone could press during evacuation, because we cannot know for sure if they will press the manual call point, let's say, in the fire level. Okay. Well, continue. And the other possibility is mechanical air release instead of natural release, the same configuration, but then we reduce the dimension of this DAC, okay, to evacuate at higher velocity that we have with a natural air release system. Okay, so you see that we have all the components. The motor is damper with the smoke, so we have the fan with the variable speed fan with the pressure sensor, standby. The motor is damper with the smoke sensor for the air intake. We have the air release, okay, and these are the components that are part of our system. And we have also the activation. As I have yet said something about that, the PDS will require a connection to the fire alarm system or specific smoke detectors to allow the activation. We need to know where the level where the fire is. Typically, the building will have a addressable smoke detection or fire detection system, okay, to EN 54, and this system will send the signal to our PDS system to be activated. Once our system is activated, the system is autonomous, operates autonomously, okay, and manages the components automatically. Okay, we can from our system give information outside, okay, that we have been activated, etc., etc. But from the fire alarm system, we only need to receive the activation system and the information that on which level the fire is there. Okay, in buildings where there is not such a system installed or not considered, imagine a refurnishment of an old building where it requires a pressurization system, but there is not a smoke detection or fire detection system. And this type of building is possible to, we can provide also these independent smoke sensors, okay, that, let me go back, will send a signal to our PDS lobby control. They will be installed one on each level and will send a signal to our PDS lobby control. So with this solution, we will activate the PDS lobby control in the fire level, and we will send information to the main control panel. So even in that cases, it's possible to solve this situation. And about the components, the last point is the manual control. This is necessary for the firefighters specifically. This manual control shall be located at the firefighter's main access or close to the building entrance. The fire brigade control panel with display for pressure, unit state, alarms, and manual activation of the system. We have these requirements both in part 6 and more specific, more detailed points in the part 13. in fact, in the new part 13, we have these requirements about that the system has to give the possibilities to the firefighters to operate the system in 3 positions. Automatic, it's when the system is waiting for receiving the signal of activation, and when the signal is received, it's automatically activated. Off, if the fire brigade want to stop the system, or on, if manual, let's say on, if they want to operate the system manually, if the system has not been activated automatically. Okay, and they need this this indicator, green light, for when the system is ready to be operated, when it's fit with energy, let's say. Red light when the system receives the fire alarm from the fire protection system. Blue when the system starts operating, and yellow if there is a failure. This is a simple manual control for firefighters for simple pressure differential kits that we also have, and this is the manual control for the firefighters for the Kitbox PDS and the Kitbox PDS Smart, that has a touchable screen with all the information. So when the fire brigades arrive, they have information about the operation of the fan, if there is a failure of the system, the state of the smoke sensor, their inlets, all the components are can be displayed here. And this touchable screen is also used for the commissioning state, because this through this touchable screen we can make the self calibration of the system. This is one of the points of our system, that during the first commissioning we press one button in this touchable screen, the system starts blowing air till it achieves the nominal overpressure, and then from this procedure the system learns how the system has to be activated the next time to achieve very quickly this nominal overpressure, and to react between the door open and the door closed condition. So this is a self-calibration solution that we include in our system. And here, through this touchable screen, you can also control, you can make the self-commissioning with the Kitbox PDS Smart. You can make all the, it's like an iPhone, let's say. When you start, you say, okay, I have one air intake, or I have 2 through flaps or through motorized dampers. I have pressurization of the staircase, or the lobbies, etc., etc. You make all the, you follow all the steps, and it's very easy to make the commissioning of the system. Other things to consider, it's about high-rise building. I have mentioned before that with high-rise building we have the situation with the stack effect, the risk of the stack effect, that even without pressurization we have this stack effect. So we will have typically in summer higher pressure in the top levels and lower pressure in the bottom levels, and we will have, without pressurization, we will have movement of air from the staircase to the levels, or from the levels to the staircase. When we start the pressurization, the system will try to solve this stack effect, or to overcome this stack effect, and try to make a more uniform distribution of pressure differences. To do that, for high-rise building, there are different possibilities. One is to install several overpressure kits to control different areas of the staircase. Imagine then we have a system at the bottom and a system at the top to pressurize this. From that system at the top, we control the overpressure on that area, and from that system at the bottom, we control the overpressure on that area. This is one possibility. We can even work with reversible overpressure kits when we have huge overpressure on the top for high-rise buildings. Then it's necessary even to evacuate air from the top. Okay, we can have multiple pressure difference sensors. With these systems, we can install a lot of pressure differential sensors connected Modbus, and then to control the overpressure by the average value, the maximum, the minimum on some specific value. And it could be also even possible with these PDS lobby controls to modulate the position of the motorized damper to supply air into the staircase and to be proportional. Okay, well, these are for some specific projects where we have these situations. About the systems, the system that we use is the Kitbox PDS and the Kitbox PDS Smart. That it's a system that is yet tested according to 12.1/6/2022. And this system includes a fan in a box, okay, together with the control panel, that has it's provided with batteries to maintain the not the operation of the fan, but to maintain the operation of the electronics of the control. Let's say we have the motorized damper with the smoke sensor. These three components came together assembled from the factory. They can be disassembled and reconnected, but they came together. And we have the remote control panel for both for the firefighters or for the maintenance or commissioning. And we have the possibility to include in the system this PDS lobby controls to control the overpressure on its lobby, or to control the operation of both the motorized supply damper or the motorized air release. The damper box or damper box smart, the system it's typically it's closed while the system is not operating to avoid air into the staircase, and when the system is activated, the damper are open. We have here the smoke sensor and the Belimo motor, and as I have mentioned before, the goal of the system is that if there is smoke around the damper, to close the damper and close very quickly and open very quickly. These dampers open and close in less than 2.5 seconds. The PDS lobby control that I have mentioned that we can include in the system, they can read the pressure difference in each single level. They are connected Modbus with the control panel, the main control panel of the Kitbox PDS or Kitbox PS Smart, and they can then control the opening both 100% or even proportional of the supply dampers, and they can manage the opening of the air release. About the Kitbox PDS Smart, because we started in 2017 with the Kitbox PDS, and we have developed the new PDS Smart. More or less in terms of hardware, it's very similar. The only difference is that this Kitbox PDS Smart, the smoke sensor is resetable, that we don't have this possibility with the Kitbox PS standard. So that's why we recommend the Kitbox PDS Smart. And the benefits, it's a quick setup, an easy setup, very intuitive. We have the positive control for air intakes, motorized dampers like louver or type hatch or wall, okay, until 3 of them, okay, and they can be placed connected to the fan or connected to a plenum, as I have mentioned before. As I have mentioned, the smoke sensor is resetable. We can operate with pressurization or depressurization, even though the new standard only talks about pressurization. There are still some countries like UK where they still operate with depressurization, and we have the possibility, if we operate with pressurization, to provide an additional performance. This is the extraction mode, that is a reversible operation of the fan. In that case, the fan has to be smoke rated, of course, but if the fire brigade wants once the fire has been extinguished, to evacuate the smoke through this system, they can use the pressurization system to evacuate the smoke. We have the possibility of connecting several pressure sensors for large staircase, choosing the mode of control, maximum, minimum, or average. We can control external sensors like reading the humidity, temperature, and wind. For instance, we had a project in a warehouse for food, where they have refrigerated rooms, and they had a corridor close to these refrigerated rooms, and they have, due to the low temperature, they have condensations on these corridors, and then they use this pressure differential system, not for pressurization during the fire. In fire, of course, they use, but for the day-to-day, they had a humidity sensor, and when the humidity rises to a certain value, they activate the system to ventilate the corridor and to avoid this risk of condensation. We can use this also to ventilate for temperature, etc., etc. And we can include a clock to program the operation of the system for daily ventilation if we want. Okay, and about the calculation, typically we have the calculation for these two situations, closed door scenario and open door scenario. Okay, the part 13 has, let's say, an annex with examples of calculation. I recommend to read this annex, because it's a good example that if one follow understands which is how the calculation is done. Okay, some things to consider is the need of safety margins that we have for door close condition calculation and for door open scenario calculation. Okay, but to do the calculation, what we use at the end of the day is we don't do it by hand. We do it with a tool that we have in our QuickFund software. Oh, sorry, I don't know what had happened. Let me see. It seems that has been a problem. Okay, now you see it. Okay, these things happens. Technology is not perfect. Okay, so we have this QuickFund software where we have these tools. Of course, we have the catalogs, the selection, information, etc. We have one part of tools where we have this pressure differential system calculation, and when we have this tool. Instead of showing that, I will now change to the other. Okay, here. Okay, suppose you see. Let me. Okay, perfect. Okay, this is the QuickFund. Once you open, you have in different language, of course, now English. Okay, here you have the part of the catalog with the different possibilities of fans. Okay, where you can, for smoke extraction fans, for instance, our axial fans typically, you will have, just to show you, okay, if you want to use it, you have here the specification of the fan, you have the models, and for each model, you will have the typical information of the fan for each specific model with the curve, with the airflow and pressure. We can change the units here, okay, but if we put on the curve, we will see the information of the airflow and the static pressure, dynamic pressure, velocity of the impeller, pitch angle, etc. Okay, and you can also you have also one part for search. Okay, if you want to search one specific fan, mention that you want ventilation units for smoke extraction fan. You know that it's the THT, for instance. Okay, that is a standard. Characteristic, you want 4 poles, F300, 1 speed, okay, and then you want static pressure, and you say, okay, 25,000, static pressure 200 pascals, and then you search, and the system will give you some possibilities, okay, green ones, the standard models, or model with customized angle, etc., etc. Okay, you can here order organized by the different values. Well, this is something that we have, but we were not talking about that. Just to show you that we have these possibilities. And in the parts of tools, okay, we have these different tools that we use for different markets. Okay, some of them are for Spanish market, some of them are standard tools. For instance, unit converter for me is very useful, or acoustic calculator, okay, or pressure drop for ducts, okay. And we have this pressurization of evacuation routes. When we go inside, okay, we have this. The first possibility is that we have we can choose which standard we use for the calculation, okay. We have EN 12101 par 6, we have EN 12101 par 13, and we have also NFPA 92, because we as a company, we work worldwide, okay, and we maintain this par 6 because there are still some countries where they have not made the change to the par 13, they are still using the par 6. We have the new par 13 because many countries in Europe has changed yet to par 13. And we have NFPA 92 because in the Middle East and the States, United States, and Central and South America, a lot of countries they use NFPA 92. NFPA 92, just to mention, the purpose is to maintain a minimum level of air pressure, 25 pascals for non-sprinkler buildings, 12.5 for sprinkler buildings, no matter if the doors are closed or open. Okay, so the key point is how many doors are open in the door open condition, because the bigger number of doors, the bigger the airflow. Okay, but the idea is slightly different to our European approach. To the part 13, okay, well, if someone wants to talk sorry, the part 6, then we can choose between A, B, C, or D class. That is the more common classes that we use for part 6. When we talk about part 13, okay, we can choose between class 1 or class 2, depending if we have sprinklers, we have this fire, these lobbies between the fire room and the staircase, etc., etc. Imagine that we are with class 1, okay. We can change the value of the density for the calculation. For Europe, we don't use that, okay, but we can change the density by changing the value or consider the temperature or the altitude or the altitude and temperature, altitude, humidity. This is for some specific cases. For instance, when we make projects for Ecuador, we are talking about 3,000 meters of altitude, then it's necessary to make this correction of density. No, it's not the case of Europe, of course. Well, okay, so we have part 13, we have class 1, for instance. Well, the first point is that we can put here the dimensions of the staircase. The dimensions of the staircase we can put if we want to include in the calculation the leakage through the walls of the staircase. In the standard, it's written that the walls can have some permeability. This is written in the part 6 and the part 13. There are some coefficients of permeability. Our program has a medium average value of permeability. So if we put here the length, the width, and the height of the staircase, the system calculates the area of walls and roof and ground of this staircase and applies this coefficient of permeability for the calculation of this leakage, both in the door closed and in the door open condition, because in the door open condition, the stair remains at a certain residual overpressure, and there are still also some leakage through these walls and also through the doors that are not open, but we can put here or not. Remember that typically the airflow in the door open condition is higher than the airflow in the door closed condition, and remember that we have a coefficient of 50% safety coefficient in the door closed calculation to consider other leakage that has not been considered in the calculation. So we are putting safety margins, okay? It's up to the designer to consider that. Here we have this, and if you see that we have maintained the 50 because it's the value that we have in the old part 6, but we have a claim here, remembering that for the new part 13, the minimum value is 30 if we want to change to 30 pascals, okay? And the air speed in the class 1 is 1 meter per second. If we change to class 2, this will be 2 meters per second, okay? We can maintain this if we want. Okay, here we have a question about the emergency elevators, if they are pressurized or not, okay? Let's consider not in that case, but if we put yes, we have to include the level of overpressure, okay, that it's for instance 30 pascals, and we need to include the area of the grill that we have in the lift shaft. The grill that we have for ventilation typically in the lift shaft is a leakage for this lift shaft pressurization, so it's important. We will have leakage from the lift shaft through the elevator doors to the lobby if the lobby is not pressurized, for instance, and we will have the leakage through this grill if there is this ventilation grill, okay? So if we have these parameters, we will need to include this, okay? Now, to make it simple, we will not pressurize the elevator, okay? And here we have the question about the landing gate or the final exit door gate, okay? This is what I have explained, that we have to consider in our calculation that if we cannot ensure that the system will be able to maintain this door closed when it's open, okay, because the problem is that when it's open, maybe we will not be able to fully close that door, okay, then we have to consider this leakage. And here, if we consider that this leakage is partially open, okay, we see that we can consider the percentage to consider. 100% will be the more conservative, okay, but this is in the hands of the designer to consider, for instance, 50% or 40%, etc., etc. Okay, indoor temperature and outdoor temperature. This is for the calculation, internal calculation of the stack effect, but it's we will maintain this as a standard, okay? And then once we have made all these parameters, we have to start creating our staircase or creating our building and creating floors. To create floors, what we do is to press here, and when we press here, we first have our first floor. You see that our first floor has appeared here, and we still do not have a flow, okay? We don't have still calculation because we have not still introduced parameters. But then here, for instance, we can name it ground, okay? And when we only have one level, this is automatically marked as the final exit level, exit floor for calculations, okay? Because the door on that levels will be calculated, will be the ones that we consider for the final exit door opening situation, okay? So with this staircase, here at the left, we have the type of doors that we have, and on the right, sorry, you don't see it. On the left, we have the type of doors that we have, and on the left, sorry, and on the right, we have the dimensions of that doors when they are open. Okay, so imagine that we have in the first level we only have, let's make it simple, one door opening to the staircase, okay, from the level, and one door opening to the outside, that will be the final, the exit door, okay? And then we can place here, which is the surface of this door will be the one communicating with the level, okay? And this exit door will be that one that opens outside, okay? To make it simple, let's put 2 square meters and 2 square meters, okay? We have this, and then of course, we will not have only one level. This will be the ground level. Let's imagine that we have another different levels above this ground level. So we go back here, we press, and we have, let's imagine the first level. Okay, we name it the first. Then we could check here, but as we don't want this level to be the final exit door, we have considered this ground level, we cannot mention it. And here you see that we only have this area of this surface, that it's open to the level, to the final room surface. Imagine here that we have not a direct communication from the staircase to the ground level, to the floor. Imagine that we have a communication through lobby with a single door, okay? You see that we have this case and we have the lobby, and from the lobby to the level we have, for instance, one single door also. That will be that situation. This is quite a common situation for staircases with lobbies, okay? So we have one door, single door, that will be that, and we have this door that will be that door here, okay? The single door communicating the staircase with the lobby, when it's open, maybe it has 2 square meters, okay? And the door, the single door communicating the lobby with the fire room, it's maybe, okay, 2 square meters. So, okay, with this we have this configuration, okay? And you see that the system had started calculating yet, okay? We have the airflow in the door closed condition, we have the airflow in the door open condition. It's quite huge because remember that we have considered that the final exit door is could be partially open at 50%. Of course, if I can put here, for instance, 10%, you see how the airflow decreases, okay? If I put here 100%, you see how it's much bigger, okay? So that's why it's very important this approach about the final exit door. Of course, if I consider that the final exit door will be closed, okay, you see that their flow is much lower, okay? So this is very important in the calculation, okay? And regarding that, I would like to mention, let's go back to this, let's go to 20%, for instance. I would like to mention that our Kitbox PDS Smart includes a system that reading the pressure evolution in the staircase, it's capable of knowing if this final exit door is it's not able to be closed. Okay, and then when we detect this situation that we have this final exit door not closed due to the residual pressure differences that we have in the staircase, what we do is for a short period of time we reduce the capacity of the fan to reduce the overpressure in the staircase, very short seconds, okay, and to allow the self-closing mechanism to close the door. Okay, so with our Kitbox PDS Smart, you here, when you make the calculation, you can put no, okay, because this door will be closed, and then the flow required, you see, that will be smaller. Okay, maybe we will have, okay, we'll pass from 24,000 to 17,000. So the motor will be smaller, the system will be smaller. So this is one advantage of our system. Okay, so we were on the first level with this configuration. Imagine that we have more levels like that. That it's quite a usual situation. I have two possibilities here. Is one to make a new level, okay, and introduce the parameters again. But if all the levels are identical, what we can do is to come to here, to the level that I want to copy, and I can make here, and here, copy, and then paste. Okay. Of course, I have to change the name here because it copies everything. So this new level will be second, but if I make another one, will be, sorry, has not changed, second. Okay, and this will be third. Okay, so we have these possibilities. Okay, here I can play with this. I can order this SFF. Well, I will change this second, and this will be to maintain the order. Okay, so you see that for this level we have the same configuration, and for this other level we have the same configuration. As you see, how when I add more levels, the drawing is modified and the airflow is also modified, and the airflow that we had in the staircase will be always the bigger one for the two calculations, in that case for the door open condition. Okay, let's make it a little more complicated. What are things what we can do? Let's delete these levels. Okay, we start from the ground level that we have, but let's imagine that I had a lobby, okay, as I had before. I had a single door of 2 square meters, and I have one single door communicating the lobby with the fire room of 2 square meters also. Here, there are other possibilities for the lobbies, that it's if I want to pressurize the lobby or not. Okay, of course, for the lobbies, well, I have single doors opening to the room, or single doors opening outside. Here the parameter is the leakage area. It's different for doors opening inside that opening outside. Okay, yeah. We can put double doors. Okay, the leakage is different. We can put elevator doors. Okay, imagine that I put an elevator, not pressurized in that case. Pressurized will be our consideration, but not pressurized. That will be, this will be a leakage through this sorry, elevator. And if I put this elevator, then is when I have to consider if this elevator it's pressurized or not. Okay, I can put here pressurized or not. Okay, and this will make different the calculation. In that case, we can consider that it's not pressurized because it's not an emergency elevator, it's a standard passengers elevator. Okay. Okay, elevator doors, or we can have also, in some countries, it's required what it's called the transfer grills. Okay, transfer grill, it's something that we include in the calculation. let's imagine a grill between, in that case, we can have it between the lobby and the room. It's not wrong here, but it's considered a calculation. Or we can have this is also between the stairwell and the lobby. Okay, transfer grill, because in some countries they require a transfer grill to ensure, specifically to ensure that there are some leakage between the staircase and the, sorry, because to ensure one transfer grill here, one transfer grill here, to ensure that there are some leakage, because they want to ensure that, because they build the door so properly that there are not enough leakage around the door, and then they need to put transfer grills to ensure this minimum leakage to maintain this overpressure. Okay, or for other reasons, because in other countries they want to indirectly pressurize the lobby through the staircase, and they install these transfer grills to have this transfer A. Okay, this is something very specific, but just to mention that if you have this leakage is included in the calculation. Okay. We can delete here and with here. Okay, so regarding the lobby, we can also include the dimensions of the lobby. Okay, if we want to include the leakage through the walls of the lobby, it's very strange, but we can do it. But we can also consider what happens if we pressurize the lobby. We can mark here, and then we have to mention which level of overpressure we want to maintain in the lobby. The point is that in the all part 6 we had that when we pressurize the staircase, we have between the staircase and the level 50 pascals, and between the lobby and the level 45 pascals, so 5 pascals between staircase and lobby. In the case of part 13, there's not such cascade decreasement, let's say, of pressure. So theoretically, we can put 30 pascals, and then we will have the same level of overpressure. Or if we want, we can maintain 25, and we will have a cascade. Okay. No matter what we put, okay, we will make the calculation. Then the system will calculate the airflow required to pressurize that lobby. Okay. This is important because this also has an influence in the airflow in the staircase. If I make this different, you see how if you focus here, please, I cannot do both things at the same time, but you see 24,000, okay? But if I pressurize the lobby, you see that on one side, I put more airflow in the lobby, but less airflow in the staircase, okay? So we have this, the tool is also, well, if we have, again, if I want to include more levels, I would include more levels, and you see how the airflow for the lobbies, it's increasing, because in that case, all the lobbies are pressurized, okay? If you have to see that all has a lobby pressurized here, okay? But I can go, if I only want to pressurize one lobby, that will be a solution. I can go and say, okay, which one, if all of them are identical, but if I know that there is one that it's more critical, then I can deselect for the rest. Okay, imagine that it's this one, okay. And you see how the airflow is changing, okay. This has a lobby, and the lobby is pressurized is here, okay. And here we have also the airflow for this specific lobby. When we make the calculation, here we will have, in that case, as all the lobbies are identical, but let's make something different. Let's make for this lobby here, we can add a double door, for instance, okay. And we pressurize the lobby, okay. And for the others that are standard, we pressurize the lobby. Okay, here, where is it? Sorry, we pressurize the lobby. Okay, here all the lobbies are pressurized, but you see that the one that has the double door that I have had more leakage, so we need more airflow. So if I had system pressurizing all the lobbies at the same time, their flow for the fan will be 8,800, and if and I will need to adjust the flow on its lobby. If I pressurize only that lobby, I will one single lobby, I will consider this. There is one question here. How to calculate elevator shaft pressurization? Okay, about the elevator shaft pressurization, let me check it. Maybe we can have here emergency elevator pressurization. Yes, okay. We pressurize firefighting. We have 30 pascals. Imagine that we have a ventilation grid of 0.4 square meters. And if we have a firefighting lift shaft grill ventilation perimeters, this is not to see how when we introduce the lift shaft, okay, we have this pressurization for automatically. When I have marked this emergency pressurization, you see that sorry here, okay, without pressurization we don't have this. When we mark here the pressurization of this 30 pascals, okay, and with the grill we have the pressurization in the elevator. In that case, as I had all the lobbies pressurized, okay, we don't have leakage from the lift shaft to the lobbies. But if I go and I do not consider pressurization of lobbies, imagine that I have this situation where lobbies are not pressurized, okay, and that okay, we will have not pressurization lobbies, and then we will have pressurization, some leakage from the from the elevator to the lobby, because the staircase is pressurized, the elevator is pressurized, the lobby knows, so we'll have leakage from the staircase to the lobby, but also from the elevator to the lobby, okay. And of course, if I change the value of this grill, I will have different values. Okay. So, well, this is mainly what the most things that you can do. There are a lot of possibilities. The transfer grills also, including the calculation, so you can put the lift shaft, firefighting lift shaft, emergency elevator pressurization. We have considered speed. Yeah, this. Okay, I think that we have seen more or less everything about the final exit door. Of course, imagine that we have this. Okay, this is a class 2, but if I changed and I put class 1, automatically the system recalculates the solution. Okay. Well, and I think that's all from my part. We are more or less at 11. That was the maximum program time for the webinar. Okay. So I would recommend if you don't have this QuickFan software to download, or ask our colleagues in Corgas to visit you and to install in your computers and to show you all the possibilities of this software, and to play with this tool with different examples to see all the possibilities of the software. Of course, when we finish the calculation, we can create a report, okay, where you can put your logo and information, and then the system will create like a report in PDF with all the information, okay, the PDF with all the information, all the parameters considered, the drawings of all the levels, etc., etc. Okay, and okay. And now I hope you are seeing, okay. And you can also add to project, okay. And if you add to the project, you can make a new project and say, okay, webinar, Corgas, accept, and then it's here, continue, and then you can put the reference. example staircase, and you add this calculation to the project, okay? And there was also the possibility, I think, to with the results, okay, go to selection, okay, and select which flow you consider. Typically will be the flow rate, the biggest one, okay, and then it will go to the selection part. Not that part, because here, let me move this. Let me go back here to selection, okay, and then we will need to change the type of system, because it will be a pressurization system, a Kitbox PDS Smart, for instance, okay, and automatically we'll have the flow that we have calculated, and we will have the pressure drop that we will calculate for the DAX, imagine 200 pascals, okay, and then when we make a new selection, we will have the Kitbox PDS that we can consider. Imagine that we have by power, for instance, this one would be enough, okay. We can open and see which is the point. Maybe it's too just, but we can have this, or we can go to the other if we prefer, and then from here we can add to project, and the same project that we have considered, adding, okay, it example, okay, add to project, okay, and with this we have in the project we have the information, and when we go to the projects part, okay, we can search the one that we have been using, webinar Corgas, and here we will have both the calculation and the kit that we have selected. Okay, can we get a record of this webinar? To be fair with you, I don't know. I will talk with my colleagues, and typically we record the webinars, and typically with the same link that you have after the presentation, it's you can accept, go into that and see the video. I think it's quite typical. Okay. By the way, what I can do is to share the copy of the presentation with my colleagues from Corgas, so they can distribute the copy of the presentation. Okay, and that's all from my part. Hope it has been interesting for you, not too boring, not too large, but I think that we have made a big review of all what is necessary to consider in the design, and also the examples of calculation. Just to finish, I have here. Okay, some examples. I don't know what happened. Okay, some examples of references. I don't know if you see now. No, not yet. But, one moment. Okay, now, well, just to finish, for information, some references of our systems in different countries. Tbilisi, in Malta, also where there are a lot of hotels in Spain, high-rise buildings, shopping centers, Romania, Lithuania, also Africa, also Uganda, Zambia. We are present worldwide, and that's all from my part. Thanks for attending, and that's all. Thank you.